This is a lecture on acid-base chemistry and mechanism writing. Here are some important definitions. For acids, we have the Bronsted acid, which is a proton donor, such as HCl, hydrogen chloride, or hydrochloric acid in water. For example, hydroxide, base, will pull off the proton from HCl to form water plus chloride anion. A Lewis acid is an electron pair acceptor. So for example, you have H+, which is a proton, or AlCl3, which is aluminum chloride. In the examples, H+ seeking a pair of electrons, so it gets them from the lone pair of ammonia, NH3, to form NH4+, the ammonium ion. In the example below that one, aluminum chloride, AlCl3, is able to pick up a lone pair from chloromethane, specifically from the chlorine atom, to form a new bond between chlorine and aluminum, which is able to give a negative charge to aluminum and a positive charge to chlorine. The reason this works is that if you think about where aluminum is in the periodic table, 3 bonds to aluminum would only give it 6 electrons. It has an empty p orbital that allows it to gain another pair. That means that that empty p orbital is an electron pair acceptor, making AlCl3 a Lewis acid. For bases, we have the Bronsted base, which is a proton acceptor. For example, as we just saw, the nitrogen in ammonia, because that has a lone pair. It can accept a proton. For a Lewis base, we have an electron pair donor. For example, again, the nitrogen in ammonia. And also, as we just saw, the chlorine in chloromethane. Electrophiles, specifically electron pair lovers, because phile means lover, is a Lewis acid. Nucleophiles, which are nucleus or positive charge lovers, are Lewis bases. Now these Lewis bases would include pi bonds. So as you can see in the example below, the carbon-carbon pi bond acts as a nucleophile and picks up a proton to form the positively charged carbon, which we will call a carbocation later, as the product. The pi bond acts as a nucleophile, and H+ acts as an electrophile. Predicting outcomes of acid-base reactions. Well, first, there's a quantitative way, meaning using numbers, to predict whether an acid-base reaction is successful. That uses the Kas, or pKas, which are minus log base 10 of the Ka, of acid and conjugate acid, to calculate the Keq, the equilibrium constant. When the Keq is equal to 1, then the acid-base reaction doesn't prefer product or reactant. So we say it's neither product nor reactant favored. When Keq is greater than 1, it's product favored. So when the reaction is complete, there will be mostly products and very little reactant left. When Keq is less than 1, it's reactant favored. So when the reaction is complete, that is, it's reached equilibrium, there will be mostly reactant and very little product. So the overall general example of an acid-base reaction, and this is a Bronsted acid-base reaction, is Ha, the acid, plus B minus the base, reacts to form A minus, the conjugate base, plus Hb, the conjugate acid. And the equilibrium constant is equal to products over reactants. Concentration of A minus times Hb over B minus times Ha. Now you could derive the equilibrium constant from 2 acid dissociation constants. The Ka for the acid, which would show products of A minus times H plus divided by Ha, and the inverse of the acid dissociation constant for the conjugate acid. So that means that you'd have Hb as the product, because you're reversing the reaction, you're not dissociating, you're associating, and B minus and H plus as the reactants. If you multiply these two terms together, the H plus terms cancel out, and you get the expression for KEQ. Thus, KEQ is equal to Ka of the acid divided by Ka of the conjugate acid. Alright, so now we've learned that KEQ is equal to the Ka of the acid divided by the Ka of the conjugate acid, and we're going to use that to be able to predict whether the reactions are going to be successful. So, given that expression, that would mean that when the numerator, Ka of the acid, is greater than the denominator, the Ka of the conjugate acid, that means the KEQ is greater than 1 and is product favored. pKa, not Ka, values of acids are given in tables and reference manuals. So let's define pKa again. pKa equals the negative log base 10 of the Ka. Now, that means that the larger the Ka is, the smaller the pKa will be. Okay, they're kind of opposite because of that negative term. Thus, stronger acids have smaller pKa values. When the pKa of an acid is less than the pKa of the conjugate acid, the KEQ is greater than 1, product favored. Let's just give an example before I show you the reaction on how to calculate whether KEQ is going to be greater than 1. Imagine that the Ka of an acid is 10 to the minus 3, and the Ka of the conjugate acid is 10 to the minus 5. Okay, so 10 to the minus 3 for the acid would mean that the pKa, negative log base 10 of the Ka, would be 3. The Ka of the conjugate acid is 10 to the minus 5, so its pKa would be 5. 3, the acid's pKa, is less than 5, the conjugate acid's pKa. Clearly, 10 to the minus 3 is bigger than 10 to the minus 5. So, that means that when the pKa is 3, that's a stronger acid than when the pKa is 5. So that's how that works. That's why when the pKa of the acid is less than the pKa of the conjugate acid, the KEQ is greater than 1 and its product favored. Okay, so let's look at the example. You have a pKa for acetylene, that's the HC triple bond CH compound, which is 25, that's for the acid, but that's reacting with the base, NaNH2, sodium amide, that forms sodium acetylide, the HC triple bond CNA, plus ammonia, NH3. Ammonia is our conjugate acid. Its pKa is 35. Again, these will be found on tables for these two compounds. What do we discover? Well, we found that the pKa of our acid is actually less than the pKa of our conjugate acid, which means that KEQ, as we've already said, would be greater than 1, and thus this reaction is product favored. In the real world, we don't have the pKa's of all of the organic compounds. It would be an enormous amount of work that is boring and nobody wants to do. And there are too many compounds that are made every single day. So, what we want to be able to do is to qualitatively determine if the Ka of an acid is greater than, less than, or equal to the Ka of the conjugate acid. That's based on structure. So if you can guess the relative Ka of the acid and the Ka of the conjugate acid, you can predict if the reaction is product favored or not without actual numbers, just based on structure. These are the acidity trends that we will use to figure out whether or not this is true. We begin with the period or electronegativity effect. As you go left to right in a row or period of the periodic table, the acidity increases as the electronegativity of the atom to which the proton is attached increases. So for example, H attached to C in methane has a pK of 50, whereas H attached to N in ammonia has a pK of 35. Nitrogen is more electronegative than carbon, and thus we see that there is a 10 to the 15th times greater acidity for the HN bond versus the HC bond. Remember that that log term means that we're talking about base 10. So when we go from 50 to 35, that's a difference of 15. So we're going from 10 to the minus 50 to 10 to the minus 35. So that's 10 to the 15th times greater for the HN bond's acidity. Water has the HO bond. Oxygen is more electronegative than nitrogen, and now the pK is 16. So we're talking about 10 to the 19th times more acidic. Really huge effects. And finally in that row we have HF, where the pK is 2. So there's a 10 to the 14th times greater acidity for HF versus HO. Now, I don't have to normally give you the numbers, but I want to just show you in this case the enormous magnitude that the periodic or electronegativity effect has on acidity. Period effect has the largest effect on acidity of all the acidity trends that we're going to look at. Really amazing effect. So we want to consider that first before we do anything else when we're comparing the relative Ka of the acid versus that of a conjugate acid. So you look at the example below. Methoxide, CH3O- is the base, and that's reacting with dimethylamine, which is the acid, to form methanol, CH3OH, which is the conjugate acid, plus the conjugate base, which is dimethylamide. NH is going to be the acidic proton in the acid because, as we already know, NH is more acidic than CH based on this period or electronegativity effect. However, NH in the acid is less acidic than OH in the conjugate acid. In the conjugate acid, that OH bond would be the most acidic bond because the OH bond, by the period effect, would be more acidic than the CH bond in methanol. Since NH in the acid is less acidic than OH in the conjugate acid by period effect, the reaction is reactant favored. So you would see very little product formation here. You would mostly see that the base and the acid would stay just the way they are. There would be no proton exchange. There would essentially be no reaction. Continuing with acidity trends, we have the group effect. In the periodic table, as you go down a column or group, the acidity increases as the atomic size increases. So, if you look at the example, H connected to O in water is less acidic than H connected to S in H2S, which is less acidic than H connected to selenium Se in H2Se. Now the reason for this is that as you go down the group, the atom gets larger and yet it still has the same amount of negative charge that it would have if it lost the proton. So if you lose a proton, right, proton's H plus, you get a negative charge. You become minus. So all of these atoms, oxygen, sulfur, selenium, will gain a negative charge once a proton is lost. So they're going to be distributing that negative charge over the surface of the atom. The same negative charge. But selenium has the largest surface area among these three elements in that group. So that negative charge, that same amount of negative charge, is spread over a very large surface area, and so its attraction to the protons is weaker. We say that the electrical field lines are longer and thus weaker. So as we proceed from selenium to sulfur, we have a smaller surface area, so that we have tighter field lines, so we have a less acidic situation because the proton is more tightly held by these field lines. And in water, we have the tightest situation. We have very short field lines, small surface area for the oxygen, and thus the lowest acidity. Shorter and stronger electrical field between the proton and an atom with smaller surface area leads to lower acidity. Longer and weaker electrical field between the proton and an atom with larger surface area leads to greater acidity. Practice problem 1. In part A, predict the most acidic proton in the following compound and explain. And so far we've only learned two effects. We've learned the electronegativity or period effect, and we've learned the group effect. So those are the only effects that you can use in your explanation of which proton you think is the most acidic in the following compound. In part B, predict the products formed by reaction with hydroxide. So you're going to write an acid-base reaction. Acid plus base makes conjugate acid and conjugate base, right? So you need to figure out the most acidic proton in part A, remove that with your base hydroxide, form your conjugate base and conjugate acid. So that's what you have to do. Now in part C, you have to figure out if that reaction is reactant favored, product favored, or neither reactant nor product favored, and explain. So that's when you use the structural prediction of relative Kas of the acid versus the conjugate acid. So use the period or electronegativity effect versus the group effect to make that prediction. Make sure you're comparing the predicted Ka of the acid versus the predicted relative Ka of the conjugate acid. Not using hard numbers, we're just using the trends we get from the periodic table. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 1. In part A, first we display all of the protons attached to the atoms. So we see that there are CH bonds, OH bond, and SH bond. To determine which proton is most acidic, we note that the CH bond is less acidic than the OH bond by period effect, whereas by group effect, the SH bond is more acidic than the OH bond. Thus, SH is more acidic than all of them, and our most acidic proton is the proton attached to S. In part B, we use our base hydroxide to remove that most acidic proton, the one attached to sulfur, to form our conjugate base plus the conjugate acid water. Part C, to figure out if this is a reactant favored, product favored, or neither reactant nor product favored reaction, we need to compare the SH bond, which is in the acid, its acidity to that of the OH bond in our conjugate acid. By group effect, SH is more acidic than OH. Thus, since our acid is more acidic than our conjugate acid, KQ would be greater than 1, and this is a product favored reaction. Continuing with our acidity trends, we now have the inductive effect. Bond dipoles creating a partial positive charge near a proton increase the proton's acidity because the partial positive charge would repel the partially positive proton. And the closer the partial positive charge is to the proton, the more acidic the proton becomes. Partial negative charge near a proton decreases the proton's acidity, which makes sense because since protons are partially positive, it would hold on to the proton, making it less likely to leave the molecule. So let's look at our examples. We have acetic acid on the left, and first we determine which is the most acidic proton. It's CH versus OH. So by period effect, we would say it's OH. We look at that only. Now, that partially positive proton is near a partially negative carbon, which is created by the bond dipoles of the CH. Hydrogen is less electronegative than carbon, therefore all the bond dipoles point toward the C, making it partially negative. That slight partial negative charge will hold on, will have a little tugging effect, holding on to the proton. Attraction of the partially negative charge strengthens the bond to the proton, decreasing acidity. However, if we replace the hydrogens with fluorines, then we have the opposite situation. Now the bond dipoles point away from the carbon toward the fluorine atoms and make the carbon partially positive. That creates a repulsion effect, and repulsion from partial positive charge weakens the bond to the proton, increasing acidity. So trifluoroacetic acid on the right is more acidic than acetic acid on the left. It's not a very big effect. As a matter of fact, inductive effect is smaller than any other effect and is ignored unless it's the only effect that matters. You can't actually decide that a proton can be removed purely by inductive effect If there's nothing else going on, there are no other effects present of all the effects we're learning in these acidity trends, then there's not enough acidity there to take the proton off. Just by inductive effect alone, that's not going to be good enough. As a matter of fact, if you look at these two situations, the only reason that the OH proton is able to be removed by any kind of base is due to the fact that it's a strong enough acid based on the period effect. If that were not the case, and we were comparing, let's say, H on a C with a greater inductive effect than H on another C, that wouldn't work. Just inductive effect by itself wouldn't be enough to remove that proton. It would be too weak an acid. There's no base strong enough to take it off purely by inductive effect. In almost every case, there's a couple of situations where if you had enough electron withdrawing effects, such as enough fluorines or chlorines or bromines attached to a carbon, that would make it acidic enough to lose its proton. But in most cases, you really cannot just have an inductive effect to create a reasonable acid. Practice problem 2. Predict the most acidic proton in each of the following compounds and explain. Okay, now we've learned period or electronegativity effect, group effect, and the inductive effect. So we can put into play any of these three effects. Remember that with the inductive effect, that's going to be considered last. You have to consider the other effects first. It may be that the inductive effect makes the difference in the end that allows you to determine which proton is more acidic, but there have to be other effects in play at the beginning. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 2. In part A, we have CH versus OH in our structure. OH will win because of period effect over CH. So we have two OHs to consider. The proton on the OH, which is closer to the partially positive carbon, is going to be more acidic because of inductive effect. You see, we had to invoke the period effect first. Now we can consider the inductive effect. And that proton, being partially positive, is closer to the partially positive carbon with the chlorines. That's going to create more repulsion on that proton and make it more acidic. In part B, we have CH versus OH versus SH. OH is more acidic than CH by period effect. However, SH is more acidic than OH by group effect. Thus, SH wins. The proton attached to the sulfur is the most acidic by group effect. Now, why don't we consider the partially positive carbon with the two fluorines on it, creating an inductive effect on the nearer proton of OH? Well, that's because the inductive effect is so weak. It's not going to be able to take the OH group's acidity and ramp it up so much that it's going to exceed that of SH. Inductive effect is just too small. We don't need it right now. We're not comparing OH versus OH. That would be acceptable. We're comparing OH versus SH, the group effect. And that's the only effect that's going to be necessary here. Our next acidity trend is the hybridization effect. Larger percent S character in hybridization on an atom means greater acidity for the attached proton. So you look at our example below, we have three different kinds of carbons with protons attached. sp with 50% S character, sp2 with 33% S character, and sp3 with 25% S character. The sp hybridized carbon with proton attached will have the most acidic proton because of the hybridization effect. That higher percent S character neutralizes negative charge around the carbon, allowing the proton an easier time being removed by a base. Last but definitely not least, in our acidity trends, we have the resonance effect. If removing a proton leads to lone pair pi resonance for the conjugate base, the more resulting lone pair pi resonance structures there are, the more acidic the proton is. So in our example, we have three different types of protons: HA, HB, and HC. If you remove proton HA, then you generate a conjugate base that can resonate its negative charge to one oxygen. There are a total of two lone pair pi resonance structures. If you remove proton HB, then you get a conjugate base that can resonate to two other resonance structures, one to the oxygen on the left and one to the oxygen on the right. If you attempt to remove proton HC, that will not lead to any resonance structures. In fact, it only has inductive effect, which is completely uninteresting, and so we just ignore it. Thus, protons HB with three lone pair pi resonance structures after you remove the proton will be the most acidic protons by resonance effect. Practice problem 3. Predict which proton or protons is or are more acidic and explain. You'll have to draw the protons if they are attached to carbon. Now, this problem may seem kind of daunting, but the first thing you want to do is show all of the protons. So if they're attached to carbons, draw in the CH bonds. If you have protons attached to different atoms, you want to consider either period or group effects. Now, if that does not apply, then what are you left with? Hybridization effect, resonance effect, and inductive effect. And which of those is the least important? Inductive effect. So you only consider inductive effect if that's all you have left. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 3. In part A, we only have CH bonds. And in all cases, the carbon is sp3 hybridized, so there's no hybridization effect. So the next thing we'll consider is resonance effect. We have two different types of hydrogens. We have the HA protons that are flanked by two C double bond O bonds, and the HB protons, which are each adjacent to one C double bond O bond. When one considers removal of a proton from position A, you get a negative charge on the conjugate base that can resonate into two different positions, one to the left and one to the right. So there are a total of 3 resonance structures by lone pair pi resonance. If you remove proton HB, you only get one additional resonance structure by lone pair pi resonance. Thus, protons HA are most acidic by resonance effect. In part B, we have two different types of carbon connected to protons, one which is sp3 hybridized and the others which are sp2 hybridized. Just based on hybridization effect, we want to exclude the sp3 hybridization and look at only the sp2 hybridized carbons. Now, 2 of those carbons are near a nitrogen and develop a partial positive charge through the bond dipoles. The other 2 carbons are further away from that nitrogen. So using the inductive effect as our final criterion, we would decide that the protons on sp2 carbons nearer the electron withdrawing nitrogen are more acidic. In part C, we have protons attached to both sp and sp2 hybridized carbons. Purely based on hybridization, then, we would expect that a proton attached to an sp hybridized carbon with a higher S character would be the most acidic by hybridization effect. Now let's figure out what makes bases strong using basicity trends. The trends for increasing base strength are the opposite for those that increase acid strength. With the period effect, basicity decreases from left to right across a period. And that's because as you go from left to right, you're increasing your electronegativity on the atom. That pulls the electrons nearer the nucleus, which is diminishing the negative charge, making the atom a poorer proton acceptor. So for example, CH3-, the methyl anion, will be more basic because carbon has lower electronegativity than NH2-, which is more basic than hydroxide. In the group effect, basicity decreases as you go down a group. You don't want the negative charge over a large surface area. That diminishes it. Remember, it's trying to grab onto a proton. You want to concentrate into a small surface area. So small atoms are stronger bases within the same group. So in this case, hydroxide is a stronger base than SH-, which is a stronger base than the much larger SEH-. With hybridization effect, basicity decreases as the percent S character increases on the basic, that is, proton-accepting atom. That means we're only going to consider the atoms that have lone pairs, atoms that can accept a proton. So in our example, the nitrogen on the left is sp hybridized, that's 50% S character, whereas the nitrogen on the right is sp3 hybridized, which is 25% S character. That's less S character, less pulling the electrons near the nucleus, which would diminish their effective negative charge, less shielding of that negative charge. So therefore, the nitrogen on the right is most basic by hybridization effect, sp3 versus sp. With resonance effect, basicity decreases the more the lone pair resonates. You don't want that lone pair moving around to different positions. That spreads out the negative charge or the partial negative charge. You want it concentrated in one spot to be a really great base. However, gaining negative charge by resonance increases basicity. Now, how does that work? If you look at our example, the nitrogen in the middle has a lone pair which never resonates, whereas the nitrogens in the bottom and left and right, those lone pairs do resonate by lone pair pi resonance, and they both resonate their electron density to the nitrogen at the top. That nitrogen not only doesn't resonate its own lone pair, but it receives partial negative charge due to the resonance of the other two nitrogen lone pairs. Thus, that central nitrogen is the most basic atom by resonance effect in two ways. One, its lone pair never resonates, and two, it develops partial negative charge due to resonance from other lone pairs. In the inductive effect, basicity decreases near partial positive charge and increases near partial negative charge. So if you look at the example, you have an anion, a carbanion, negative charge on carbon, in which the negatively charged carbon is further away from an oxygen atom, which is electronegative, and the negative charge on the carbon directly attached to that oxygen is less basic. So why does this work? Because you have bond dipoles, which is pulling electron density away from the carbon that the oxygen is attached to, giving it a partial positive charge. You don't want to have the negative charge where carbon is developing a partial positive charge. That diminishes the negative charge. Imagine adding a little plus to the minus. It's going to make the negative charge shrink. And that's why having the negative charge further away from those bond dipoles, further away from the partial positive charge, gives that negative charge greater basicity. A neutral atom is less basic than the same atom with a negative charge. That's what you'd probably expect. I mean, negative charge is going to be the most attractive to something with the opposite charge, which would be a proton. Thus, in our example, hydroxide is a stronger base than water. Practice problem 4. Circle the most basic atom in each of the following molecules and explain your selections. So, now remember, you're looking for atoms that have lone pairs. Those are the only atoms you're going to consider. You're also going to apply a trend, one of the trends that we've learned. Remember that the basicity trends work in the opposite way to the acidity trends. Also, if there is any resonance into a benzene ring, never consider a possible way of assigning a lone pair to be a lone pair on an atom that used to be in a benzene ring via resonance. That is, you can't think about destroying the benzene ring's resonance. You can't think about disrupting the alternating pi bonds just so you can put a proton on the benzene ring. That's not allowed. Leave the benzene ring alone. Sure, it can allow you to resonate via lone pair pi resonance, but you can't actually put a proton on the benzene ring, at least not at this level of the course. So benzene rings, okay for letting you get lone pair pi resonance, but you don't actually get to protonate the carbon atoms in the ring. Answers to practice problem 4. In part A, we have two atoms with lone pairs. They're both oxygen, and they both have negative charges. The oxygen on the left side is able to resonate its negative charge into the benzene ring through lone pair pi resonance. That means it's going to be a poorer base. The oxygen on the right side has no resonance, so by resonance effect it should be the stronger base. Now let's point out again that negative charge can resonate into the benzene ring, but even though I can draw a lone pair and a negative charge resonating throughout that ring, I don't consider any of those carbons with a negative charge to be places I can actually protonate. Therefore, those are not going to be considered basic atoms from the perspective of circling the most basic atom. And again, the most basic atom will be the oxygen on the right, most basic atom by resonance effect, no resonance. Part B, we have two atoms with lone pairs, a nitrogen and an oxygen. This is simply the period effect. The less electronegative atom, which is nitrogen, will be the most basic atom by period effect. Now we come to mechanism writing. What is a mechanism? It's a story, it's a narrative, it's a description of how reactants become products. They are the steps that lead from reactant to product in a reaction. We use arrow notation to describe electron flow in bond forming and bond breaking events. The arrow shown below on the left is a 2-electron arrow. There's a 2-electron source, which is a nucleophile or breaking bond, going toward an electron sink, that's the end of the arrow hook, which is an electrophile, leaving group, or a lone pair acceptor. For example, the electron source, our nucleophile, can be hydroxide, and then that arrow goes toward a carbon atom with a partial positive charge. That's the electron sink or electrophile. That breaks the bond between carbon and chlorine. We show the electron flow toward the chlorine. The source of electrons is our breaking bond when we start the arrow from the middle of that bond, and our electron sink is the leaving group, and the arrow ends at that atom, which is the chlorine atom. Our products are shown: methanol, CH3OH, plus chloride anion. This is an example of a one-step mechanism, but mechanisms can have many steps leading from reactants to products. Here's an example of a two-step mechanism. Methoxide, CH3O-, is the nucleophile. The electrons flow from the negative charge to the partially positive carbon in the double bond. That carbon is the electron sink or electrophile. Then the pi bond breaks, and the electrons flow from the source of electrons, which is the pi bond, toward the electron sink, which is the oxygen, that's the electron pair acceptor. That forms an intermediate which decomposes by the source of electrons now being negatively charged oxygen, forming a new pi bond. So the electrons are shown flowing toward the middle of the bond and displacing chloride. So electrons are shown flowing from the carbon-chlorine bond as the electron source toward the leaving group chloride. Note, if the electron source is creating a pi bond, as we saw in the intermediate, you always end the arrow in the middle of the acceptor bond. Okay, now we're going to look at one-electron flow, or radical chemistry. So our mechanisms are going to involve one electron going from one atom to another, or from one bond to an atom. So we use a new arrow which has a single hook, a little fish hook, and In the bond breaking event, one of these half arrows or fish hooks goes toward atom A, giving atom A 1 electron, and the other goes toward atom B, giving atom B 1 electron. So it's an even split of that bond. In the bond forming event, 1 electron comes from atom A, which is a radical, unpaired electron found on that atom, and 1 electron comes from radical B to form a bond. In the mechanism shown below, we first break the bromine-bromine bond using our half arrows, forming 2 bromine radicals. Then a bromine radical will break a carbon-carbon pi bond. So there's a half arrow that goes toward the bromine and is met by a half arrow from the bromine radical. And there's another half arrow which goes toward the carbon to the left, showing that that carbon is accepting an unpaired electron. And the result is an intermediate where the carbon is a radical, and there's a new carbon-bromine bond. In the last step of this 3-step mechanism, the carbon radical breaks the bromine-bromine bond, and you show that by showing the source of electrons as being the bromine-bromine bond. So since it's breaking, one half arrow goes to the bromine atom, and the other half arrow meets up with a half arrow from the carbon radical. That's the bond forming event. So we generate a carbon-bromine bond and a bromine radical in the final event. Practice problem 5. Draw the correct arrow notation for the steps in each mechanism. At this stage, you can't predict the mechanism. I have to give you the steps in the mechanism. And then you're simply going to use electron sources and electron sinks to show the correct arrow notation as bonds are forming and breaking. That's your only goal. They're either going to be full arrow 2 electron arrows, or they're going to be half arrows for 1 electron transfer. Answers to practice problem 5. Okay, how do we know what type of arrows we need to use? Well, in part A, we have a carbocation, a positively charged carbon, and bromide, Br-, as the products of the first step in the mechanism. The only way that can occur is if 2 electrons were to flow from our electron source, the pi bond, toward our proton, and then the HBr bond as the new electron source broke off and gave electrons to our electron sink, Br. Both electrons being transferred from the pi bond to the proton would give a positive charge on carbon, and both electrons going to Br would give a negative charge on bromide. There are no radicals present, therefore these are full arrow notation mechanisms. In the final step, bromide, Br-, is the electron source, and the electrons flow from that source to the electron sink, which is the carbocation, C+. In part B, we again have full arrow notation, 2 electron transfer, because our final product shows a negative charge on the oxygen, so it had to gain a lone pair, 2 electrons. So the hydroxide is our electron source. The electrons flow toward the partially positive carbon, which is our electron sink. The electron source that is going to provide electrons to O is that carbon-oxygen sigma bond. The electrons flow from that source. Notice the arrow has to be from the middle of the bond to the oxygen, which is the electron acceptor, electron pair acceptor. That gives us our final product. Part C is our only radical case. We start with the bromine radical, which is going to form an HBr bond by breaking the CH bond. So, half arrow goes from the CH bond meeting up with the half arrow from the bromine radical, and another half arrow goes toward the carbon atom, showing that it's accepting 1 electron. And our products are the carbon radical and HBr.